Hello engineers, welcome back. In this video, we're going to talk about a special type of tree called binary trees. I hope you're ready. Let's get started. So in this video, we're going to look at what binary trees are. We discuss the structure of a binary tree and then we'll perform all these operations in C++ and then we'll discuss time complexities. Okay, so let's get started. So what are binary trees? Binary tree, it is a tree with one condition. Tree with one condition. The condition is max 2 children per node. In the previous video, we saw a general tree where there could be any number of children for any node. Here we will add a constraint that there can only be 2 children per node. Okay, so let's see how the structure of a tree looks like. So if this is my node, I can have a maximum of 2 children. 20 and 30. Okay, so the parent node is called the root node. This is the first node in the tree. And then this one is called the left node. And then this one is called the right node. And then 20 can have its own left node, let's say 40, and it can have its own right node, let's say 50. Okay, so this is how a binary tree looks like. Okay, so there can be a maximum of 2 children per node. Now let's discuss how to do all these operations. So let's start with insert. So if there is nothing in the tree, we will insert the root node, and the first element after the root node will be added to the left child of the root node. So first the left is filled, and when the left is filled, the new node will be added to the right of the root node. So this is the right. After that, if there is any node to be inserted, we will insert it at the left of 20. And if there is a node after that, we will insert to the right of 20. If there is a node after that, we will insert to the left of 30. And the node after that will be added to the right of 30. Okay, as you can see, the insertion is happening at levels. First, this level got filled. There can be only one node at the root, and then the second level got filled, 20 and 30, and then the third level got filled from left to right. So this is level order inserting. So if there is a new node, first we will check in the top level if there is any left node or right node available to be filled, then we will fill it. Otherwise, we'll move to the next level and then we'll repeat the process. Okay, once we find a spot, we will add to it. Otherwise, we will increase the level and add a new node at the new level. Okay, so this is level order insert. Now let's discuss search. Search is again implemented using level order search, because if, let's say, I want to find the node 70, I will check for the node at level 1. If I find it, okay. Otherwise, I will go to the next level. I will check here. Otherwise, I will go to the next level. I will check here, and then I will find my node and I will return it. Okay. So again, search is at level order search. Now let's discuss display. Display can be of 3 types. One is pre-order, another is in order, and the third one is post order. Actually, there can be a fourth one as well, which is called level order. So we can print the tree in 4 different ways. So let's discuss pre-order. If this is my baby tree, 10, 20, 30, and if I want to display this tree in pre-order, first the root node will get displayed, then the left node, then the right node. Okay, so root, left, and then right. In order, first the left node will get displayed, 20, then the root node, then the right node. So left, root, and then right. This is in order display. And then, as you can guess, in post order, First, the left node is displayed, then the right node is displayed, then the root node is displayed. So first the left node, then the right node, then the root node. This is post order. And then in level order, we already know this. First, level 1 nodes will get printed, then level 2 nodes will get printed. So this is not in any order with respect to left or right children. This is with respect to level 1 and level 2. First, the level 1 nodes are printed, then level 2. If there are level 3 nodes, then they will get printed from left to right. Okay. So this is level order display. So all these are different types of display methods. So we will code all this and see. And then let's discuss remove now. Now for remove, again, this is a tricky situation because we need to maintain the structure after removing. So let's say I want to remove the node 20. We need somebody to take the place of 20 so that the binary structure is retained. Okay. So let's say I'm removing 20. Who can I put here? Can I put 40 here? If I put 40 here, then it will look like this, right? 10, 40, and then 50, and the remaining nodes. But this is not a binary tree structure because 40 is not having uh, a left node, but it is having a right node, which is not a structure of binary tree. As we discussed, we need to have the nodes inserted from left to right. So we cannot have this type of structure. So what can I do? So can I put 50 here? No, again, same problem. It will have a left node, but not the right node. Again, it will break the structure. So who can I put here? So the solution is we will take the last node, rightmost node in the tree and put it there. So the structure will now look like this: 10, 70, 40, 50, 30, 60. Now this is still a binary tree because if we look at it from first level, there is one root node. From the second level, there are two nodes, left and right. Very good. And then in the third level, there is a left node and there is a right node and then there is a left node. If a new node comes in, we know where to put it. We'll put it here. And the binary structure is retained. Okay. So in order to remove anybody in the tree, we will first find the rightmost node and replace it. So that will be the removal strategy. Okay. So let's code all this in C++. So let's begin. So I have made a new file called binary tree and I've created the base template. Now we can get started. So what do we need? First, we need a tree node and it will have a value holder, and then it will have one holder for the left and it will have one holder for the right. And then let's create the constructor which will take in a value and this will be initialized. Let's initialize the pointers to null. Okay, my node is ready. Now let's build the tree. Binary tree. It will have a root node and let's expose some methods. First is the constructor which will point root to nothing. So this is the constructor, and then let's discuss our methods. We need insert which will take in a value. We will have a remove method which will also take in a value, and then we will have a display method. Okay, and how do we create this tree? We simply say bt. Okay, so let's start with insert. For insert, what do we need? We need to first check if root is empty. If root is empty, then we will insert our first node. So let's create a new node and point it to root. So root equal to new node of value and return. Okay. Otherwise, we need to find a spot for the new node. So we need to go one level at a time and find the empty spot. So for that, we will use a queue and push the root to the queue. And while queue not empty, this is what we'll do. We'll add the root node first. We will check if the left of root is empty or if the right of root is empty. If the left is empty, we will add a new node there and we are done. If the right is empty, we will add a new node there and we are done. If it is not empty, we will add it back to the queue and continue the process. So let's get the element out. So now we got the root node out. We are checking if front arrow left equal to null ptr, then we found our place. So we will do this part, which will be front arrow left equal to new node and return. We are done here. Otherwise, we will add this to our queue. Front arrow left should be pushed to queue. So queue dot push front arrow left. We will repeat the same thing for right. If front arrow right equal to null ptr, then front arrow right equal to new node and return. Otherwise, we'll push the right node into the queue and queue dot pop. We can pop the first element. We can pop it here itself. Okay. So this is the insert logic. First, we'll try to insert at the root node. Otherwise, we go left, find a spot. We go right, find a spot. And we are doing level order search for the empty spot. Okay. So this is insert. Now let's talk about display. For display, again, we'll check if root is empty, nothing to remove. We will simply say tree is empty, return. Otherwise, we need to find the rightmost node, right? So we need to find the rightmost node called 70 and we need to replace it here. Okay. It's possible that the rightmost node can have its own children. I'll show you. Let's say our tree is like this. Okay. Now, who is the rightmost node? Rightmost node is 30. Right? Rightmost node is 30, who is not having a right child. And 30 has a child of its own. We need to retain this child as well. Okay. So what we can do is when we are removing 30 and moving it to this position, now it's like this. Now 20 is gone, 30 is here. Now what to do with this 60? This 60, we will simply attach it to the parent. Okay. We will simply attach it to the parent. Like this. Now our binary tree state is retained. Okay. So let's see how we can do this. First, let's build a function to get the rightmost node and a parent. We need to find the parent as well. In order to attach this child to the parent, we need to get both the right node and the parent. So we can use the concept of pairs here. So let's write a method to get the rightmost node and parent. We can use the concept of pairs for this, since we are getting two elements out of the function, and they will be part of the utility library. So let's see how the syntax looks like. So this will return a pair, and both will be node pointers, right? And this will be the method. So what do we need? First, we will check if the root is available or not. If root equal to null ptr, then we need to return a pair of null pointers. So we can say make pair null ptr null ptr. Okay, so this will return a rightmost node as null and parent as well as null. Okay, otherwise what do we need to do? How do we find the rightmost node? We started the root, we go right. If that is the rightmost node, we stop there. Otherwise we go to the right of that node. So we go right, and then we find the rightmost node. Okay, so we will need two things here. First is a parent node, and since we are starting at root, the parent of root will be null ptr. And then we'll need another one for current, which will be the root node. So we're starting at root, and then when we find the rightmost node, we will return both current and parent. So while we'll keep going right. And while we are going right, we will keep updating the parent as well. Okay. So once this loop is finished, we will reach a state where we are at the rightmost node in our current, and whatever is the parent of that node will be in parent. Okay. Now we can return this. Return make pair parent current. Okay. Now let's see how we can extract all this. So we are getting a pair. We're getting a pair. Both are of node star. Let's call it parent and okay. Now let's extract them. So we need a node pointer which is called rightmost node. This will be part of the pair in parent and node dot first. And another one will be parent, which will be part of parent and node dot second. I hope I got the order right. Let's see. We are making parent first and then current. So this is first, this is second. So parent is first and then this is second. Okay. Now we found our rightmost node and the parent. Now what do we need to do? We need to find the node where this value exists. Okay. For that we will implement a search method, which will take in a value. So if root is empty, return null ptr. Nothing to do. Otherwise, we will do level order search. So we will take a new queue. And we will push the root node here. And we will keep checking one level at a time. While queue not empty, we'll get the first element out. So we check here. If front arrow value equal to the given value, then we can stop and return front. Okay. Otherwise, if front arrow right is not equal to, sorry, let's start with left. If front arrow left not equal to null ptr, then q dot push front arrow left, and we will repeat it for right as well. If front arrow right not equal to null ptr, q dot push front arrow right. Okay, and we can pop this after done. Now here we can do some optimization. Instead of pushing left and right, we can do a simple check. If front arrow left arrow value, since we have access to these elements, why not check here itself, right? Equal to given value, then return front arrow left, directly return from here. We can do the same thing for right as well. If front arrow right arrow value equal to value, then return front arrow right. Okay, so we are checking three things. First, the root node, and the left node and the right node. If we find a value, we will return it. Otherwise, we will add the elements to the queue and we will repeat level order search. Okay, now we have our search. Now let's see. So this will be node, let's just call it node, and this will be part of search, and this will take in value. Okay, now we found our rightmost node, the parent of the rightmost node, and the node that we want to remove. Let's say we want to remove 20 from here. We want to remove 20. So we found 20, we found 70, and we found 30 as well. We have all these three elements. So now what is our algorithm? We will simply replace 20 with 70 first. Node arrow value will be rightmost node arrow value. Okay, so that is done. Now we can remove 70, but before removing 70, we need to attach the children of 70 to the parent, like here. If there is a child, we need to retain this child and make it to the right of the parent. So parent arrow right equal to rightmost node arrow left. Okay, this will always be on the left side, because if it was on the right side, then that would become the rightmost node, right? Which is not what we need. We need the rightmost node where right is empty. Okay, so this is done. Now we can safely remove the rightmost node and return. Okay, quick recap. What did we do? First, we got the rightmost node and parent. So we went down one level at a time. We got the rightmost node and parent. Next, we extracted the parent node and the rightmost node. And then we went implementing the search to find the value, the node to be removed. So we went level order search and we found our 20. Then we replaced the value of 20 with the value of 70. So 70 is now here. Now the tree is like this. Next, parent arrow right is rightmost node arrow left. So this was the rightmost node. It's left was empty. So this will be null pointer. So the parent's right is now pointing to null. So we have removed the connection. So that is fine. If there was any node left hanging, that would have been attached here. That is also fine. And then delete rightmost node. So rightmost node is deleted from memory, and then we return. Okay, so that is remove. Now let's talk about display. Display, as we discussed, there are 4 types of display: pre-order, in-order, post-order, level order. Let's implement them one by one. Let's close all this. First, let's do pre-order. We will take in a node to start our printing. This will usually be the root node. And then if node is empty, nothing to do, we simply return. This will be the base case. Otherwise, we implement recursion. So for pre-order, first we print the node, then go left, then go right. So we print the value, then we go left, and then we go right. So this is pre-order. So the printing is happening first, and then go left, and then go right. Now let's do in order. Again, same process. If node is empty, return. This is the base case. Otherwise, call recursion. So for in order, first we go left, and then we do the print, and then we go right. So this is in order. Now let's do post order. Again, if node equal to null, return. Otherwise, post order, right? First we go left, then we go right, and then we print. This is post order. You can remember it like this. See the cout. Cout is at the beginning, which is pre-order. Cout is in the middle, which is in order. Cout is at the end, which is post order. Simple. Next, let's also do level order. We already know how to do this. We start at the root node. So we take a queue. So let's do a check anyway. If node is empty, simply return, nothing to do. Otherwise, there is at least one element. Let's add it to the queue. Queue dot push node. And while queue not empty, we will start printing. First, let's get the element out. And print it. And then pop. Since we got it out, we can pop it. So now we check if there are any left or right elements. If front arrow left is not equal to null ptr, then q dot push arrow left, and then we repeat it for right as well. Done. So this will take care of level order printing. Okay. So I think that's it. Now here, let's call these methods. Cout pre-order display pre-order. Then let's do cout, and then let's repeat this. In order display, in order, post order display, post order, and then level order display, level order. Okay, so those are our public methods. So let's close all this so that it's clear. Okay, so we have three public methods: insert, remove, and display, and then these are our helper methods in the private space, and this is our tree node. Okay, I think we got everything. Now let's do our operations. Let's do bt dot insert 10. Actually, we can just print this tree. build this tree: 10, 20, 30, 40, 50, 60, 70. 20, 30, 40, 50, 60, and 70. And then we can do display here, and then we can do remove. Like we discussed, we can remove 20, and then we can do display again. Okay, so this will be our operations. So let's run it and see. So our code is working fine. Let's just add a cout after removing 20. Okay, now let's just verify if our output is fine. So let's check level order display. We have 10, 20, 30, 40, 50, 60, 70, which is what we need here, right? 10, 20, 30, 40, 50, 60, 70. And then after remove, we have 10, 70, 30, 40, 50, 60. We have 10, 70, 30, 40, 50, 60, right? So our logic is working fine. So you can verify the same thing with other displays as well using the same in order, pre-order, post-order logic. Okay. So we are done with this. So in this video, we have seen what are binary trees, what is the structure of a binary tree. We have performed all these operations. And then now let's discuss time complexities. So first, let's do search. Search is O of n because we don't know where the node will be. We need to check all nodes. And then insert is also O of n because we need to find the spot for putting the node. We are looking at one node at a time. Again, this is O of n. And then all these displays are O of n because we're printing every element. And then remove. For remove, what are we doing? For remove, we are doing one search to find the node, which is O of n. And then another search to find the rightmost node, which is like going right, right, right. So that will be log n. So comparison of these two will give us O of n. Okay. So all these operations are O of n. Okay. So those are the time complexities. So that is a general binary tree. Okay. So that is it for this video, guys. If you have any questions, you can definitely ask me. We learned about binary trees today. So don't forget to leave a like if you found this helpful. Do comment if you have any questions or suggestions. Don't forget to bookmark the playlist and share it with your friends. Thank you so much for watching. I will see you in the next one. Cheers.